All right, so in the previous video, we were looking at how to apply the fundamental theorem of calculus, part 2, to evaluate definite integrals by finding antiderivatives. Now, we were dealing with antiderivatives in sections 4.1 and 4.2. And in 4.2, we looked at certain cases which show up very often where the integrand is very difficult to find an antiderivative for the way that it's written initially. However, if you use what's called U substitution, which we talked about in 4.2, that can make those integrals easier to evaluate. So we're going to do that here because U substitution is a common technique and we want to be good at using it. But I want to do it in the case of definite integrals. And there's something important to pay attention to if you're going to use a U substitution with definite integrals. The issue is that when you're doing a definite integral, the limits of integration, like in this one, I have 0 and 2 as my limits of integration. Those are values of x. If you think about what they represent, if we were to graph this function in here and then find the area under that curve, we're specifically finding the area between that curve and the x-axis over this interval on the x-axis. So where x is equal to 0 and x is equal to 2. Those are x values. If I'm going to make a change of variables, then specifically if I'm changing from x's to u's somehow, I need to think about how these limits of integration would change as well. They're going to be converted over to whatever their corresponding values of u would be. So in these examples, I'm going to show you how that works. Let's start with this guy. For part A, we want to integrate from 0 to 2 this function, x times the square root of x squared plus 5. Now this is a pretty classic type of U substitution problem, and you've seen this already. In this case, it makes the most sense to choose the radicand to be u. So that would be u equals x squared plus 5. Okay. Now du would be 2x dx. And remember, at this step, we look at what we have on the outside of that radical. It's just an x with a dx over here, pretty close to what we have, but the 2 is not showing up anywhere. So I multiply both sides of this by 1/2 so that it does match what I want it to match. 1/2 du is equal to x dx. Okay. Now that gives me a great way to change my integrand into something that's easier to manage. But what I now need to do is change these limits of integration. So again, remember, these are x values. So for my lower limit, I need to use what I defined u to be in terms of x, and I need to plug the lower limit of integration in for that x. So u would equal 0 squared plus 5, which equals 5. This will become my new lower limit of integration. My upper limit, I do the same thing. I plug in the lower limit of upper limit of integration, which was 2. So I get u equals 2 squared plus 5, which is 4 plus 5, or 9. That's my new upper limit of integration. Okay, so I'm going to rewrite this integral in terms of u and with these new limits of integration. Lower limit is 5, upper limit is 9. And then here, remember that we have this 1/2 that showed up when we found our du, and we know from experience that 1/2 can be brought out of the integral, so I'm going to do that here. And then I have the square root of u times du. That accounts for everything that's in my integrand. So I'm going to write that as u to the 1/2 du. This is going to give me this 1/2 times, add 1 to my exponent, so u is going to give me, or it's going to become u to the 3/2. And then here I'm going to have the reciprocal of this, so times 2/3. Notice we get some cancellation happening there. And we're going to evaluate this from 5 to 9. Now notice here I didn't put square brackets around the whole thing. And the reason why is because I only have one term here. when you're doing a definite integral and you get to this antiderivative step, once you get it down to just this single term, it's okay to put a vertical bar there with your limits of integration as opposed to a square bracket. But if you have multiple terms, more than one, then you need square brackets. So now we've seen both ways this could look. From the cancellation, I'm going to get 1/3. And I'm going to keep that factored out because both of my terms, when I plug in my 9 or my 5, will have that 1/3. I can factor it out. And then I'm going to have 9 to the 3/2 power minus 5 to the 3/2 power. Okay? 5 to the 3/2 power is not something I'm going to be able to simplify. I could plug it into a calculator and get a decimal, but then I would have to round it, and I don't want to bother with that. So I'm going to just leave that alone, but I can simplify this one because this is the square root of 9 cubed. The square root of 9 is 3, and 3 cubed is 27. So this becomes 1/3 times 27 minus 5 to the 3/2 power. I could leave my answer that way, or if I chose to distribute the 1/3 in, 1/3 times 27 is just 9, minus, and then this won't give me any simplification, but I could write 5 to the 3/2 power over 3. That's a valid way of writing that as well. So that's my answer. And again, as you've seen throughout this course, and I imagine other courses as well, in math, we prefer to leave things in this form as opposed to plugging that into a calculator and getting some kind of a decimal, unless it's an application problem that calls for that. Okay, let's take a look at B. Here's B. I'm looking at the integral from -1 to 1 of 6x cubed over x to the 4th plus 1. And what we have seen throughout the stuff we've done with antiderivatives and U substitution specifically is when you have a rational function and the degree of your denominator is 1 greater than the degree of your numerator, oftentimes, not always, but oftentimes the best choice of U is the entire denominator. Let's try it. If U is equal to x to the 4th plus 1, then what is du? du is equal to 4x cubed dx. Now, if you notice, we almost have that. I don't have a 4x cubed, I have a 6x cubed. But we have found a way to fix that. You multiply by the reciprocal of the number here times the number here. So 6 over 4, or 2/3. I'm sorry, 3/2. If I multiply both sides by 3/2, I get 3/2 du equals 6x cubed dx. Okay, so now we're going to change the integrand, and I'm going to change my limits of integration, but I'm not going to write it out like I did here. I wanted to do that one time so you could see where those values are coming from, but now I'm going to talk through it, and something very interesting is going to happen in this example. I'm going to take my lower limit of integration, -1, and I'm going to plug it in for x here to get the corresponding value of u. If I take a -1 and plug it in for x, -1 to the 4th power is +1 plus 1 would be 2. The upper limit of integration is 1, and when I plug a 1 in here, I also get 2. Well, I'm going to return to that in just a second, but now let's rewrite our integrand. My denominator is now just u. My numerator is du, but times 3/2, and we can pull the 3/2 out, as we know. So this is du over u. Even though that's an easy integral to evaluate because we know that we would get the natural log of u, I don't even need to bother with that. I know immediately that this is equal to 0. And how do I know that? In our properties of definite integrals, in the previous section, we had one property that says if you ever take the definite integral of any function and your upper and lower limit of integration are equal to each other, then that is always equal to 0. So I get to use a property of definite integrals here instead of having to go through the fundamental theorem of calculus. That was really, really nice to remember. That made that problem go faster. Let's try the last one, part C. I'm taking the definite integral from 0 to 2 of 2x cubed times the quantity x squared minus 4 to the 5th power dx. This problem I could do by expanding that out, and I would get a 10th degree polynomial, and then I would multiply everything in that 10th degree polynomial by 2x cubed, which would give me a 13th degree polynomial, and that would be horrendous because I would have a gajillion terms that I have to deal with. Just multiplying that thing out would be a beast. I don't want to do all that. But we have seen that you can do problems like this using u substitution by setting u equal to the thing in parentheses. I'm going to set u equal to x squared minus 4. Now, I have to find du, and if you notice, du is equal to 2x dx. Okay? That looks similar to what I have, but it's not 2x dx that I have. It's actually 2x cubed dx. So how do I deal with the fact that this is an x cubed? Well, it would be nice if I could multiply this thing by x squared, because then that would give me 2x cubed. And we've actually seen a way of doing that. Over here, I have an x squared showing up in relation to u, but it's not isolated. If I solve this for x squared by adding a 4 to both sides, I get that x squared is equal to u plus 4. So if I wanted to multiply both sides by x squared, that would be the same as multiplying both sides by u plus 4, since they're equal to each other. Let me do the u plus 4 on this side, and its equivalent x squared on the right side. That's equal to 2x cubed dx. We've seen this before in 4.2 when we learned about u substitution. Sometimes you have to manipulate the original definition of u to make it work into your integrand. Okay, so now let's look at the integral again up here. I have to change this into a function of u using the substitutions that I've created down here. And I also need to change my limits of integration. So looking at my limits of integration now, I have 0. If I plug that into my lower limit of integration, oh, I'm looking at the wrong place. If I plug 0 in, sorry, not my lower limit, if I plug it into this, 0 squared is 0 minus 4, that would be negative 4. So my lower limit of integration is negative 4. My upper limit of integration, I'm going to take this 2, plug it into the x. 2 squared is 4, minus 4 is 0. Okay? Now, I need to rewrite the integrand in terms of u's. So the thing in parentheses here, well, let's start with this. The 2x cubed dx, which I have down here, is equal to u plus 4 du. I'm going to write the u plus 4. I'll put the du out here, but I want to put something else first. Over here, I have x squared minus 4 to the 5th power, but that thing in parentheses is what we defined u to be. So it's actually just u to the 5th power. Here's the du that I said I was saving for later. Distribute the u to the 5th in, and I'm going to get u to the 6th plus 4u to the 5th du. And now we can do the integration. I need brackets for this one because I have 2 terms. Remember, add 1 to the exponent and multiply by the reciprocal, so 1/7 u to the 7th power there, plus 4u to the 5th power, we have to take an antiderivative, add 1 to the exponent, which is a 6, multiply by the reciprocal, so 4 divided by 6, or 2/3. And that's going to be a u to the 6th power. We go from negative 4 to 0. Okay? Now I plug in these values. So 1/2 times 0 to the 7th power is 0, plus 2/3 times 0 to the 6th power is still just 0. If you haven't noticed yet, we like it when zeros show up in our limits of integration. It makes life easier. Okay? Now, I need to do the rest of this. So minus, we have 2 terms, so make sure you put that square bracket there. Plug a negative 4 in. 1/2 times negative 4 to the 7th power plus 2/3 times negative 4 to the 6th power. I didn't work this one out ahead of time, so I'm going to do it on my calculator over here real quick. All right, so we said that we have 1/2 times -4 to the 7th power plus 2/3 times -4 to the 6th. Okay. However, there is this negative in front of it. So when I plug it in here, I'm going to get a negative number because a negative number to an odd power gives me a negative. And I get a negative number that kind of has a greater absolute value than the positive number I get over here. So this sum comes out to a negative. But then applying this negative will make it positive. And what I end up with, as a decimal at least, is about 5,461.3 repeating. You could write that as a fraction as well, but that's the answer as a decimal. Notice I didn't round, I used the repeating symbol, so that is an accurate answer. Okay, so that's a little bit of practice on using U substitution with the fundamental theorem of calculus. Remember to change those limits of integration. Okay, like this. Here's another example where we just take a kind of a different perspective on on these functions, or on the fundamental theorem of calculus. This is the graph of f prime. So this is the graph of the derivative of a function f. Okay, and it says if f of -6 is equal to -2, find each of the following. What is f of -3? What is f of 4? So remember, what we're looking at here is not the graph of f. It's the graph of f prime. If it was the graph of f, I would be able to find these very easily, and I wouldn't even need this extra information. I would just find -3 on my x-axis, find the y value of the corresponding point, and that's what f of -3 would be. But that's not what we're looking at. This is the graph of the derivative. However, I do know this. If I take a definite integral from, let's use the number that was given to us, -6, to the number that we're looking for, -3, of f prime of x dx, I know that that is equal to f of -3 minus f of -6 because of the fundamental theorem of calculus, right? Remember, that's the relationship. This f is the antiderivative, or it's an antiderivative of f prime. So this is from the fundamental theorem of calculus, and one of these two values we already know the value of. F of -6 is equal to -2 according to the problem. So if I'm subtracting -2, this is the same thing as f of -3 plus 2. Now, because it's f of -3 that I want, I could subtract 2 from both sides here, and I could write this as -2 plus the definite integral from -6 to -3 of f prime of x dx, and this is what f of -3 would be equal to. I'm going to write it there. But I haven't figured this out. I need to know what that definite integral is. Fortunately for me, I know that definite integrals can be interpreted as areas between a curve and the x-axis. So I can deal with this by looking at the graph and finding areas. Here's -3, right there. Where's -6? It's right here. So we are looking at the area of this triangular region right here, okay? That's equal to, again, we have this -2 right here. What is the area of this region? 1/2 base times height. So if I look at the base, 1, 2, 3, it's got a length of 3. If I look at the height, it's going from 0 all the way down to this, which is -4. So that would be a height of 4. So 1/2 times 3 times 4. But because the area is beneath the x-axis, I treat it as negative area. So it's -1/2 times 3 times 4. That's the area of that region right there. Okay, 3 times 4 is 12, half of that is 6, so I have -2 minus 6, which is -8. So f of -3 is -8. Okay, that's part A. Part B is similar. I just have a different value of x. So if I want to find f of 4, once again, I can set up this definite integral using this value that I have here, f of -6 equals -2. So let's set -6 as my lower limit of integration, and this time I'm going to set 4 equal to my upper limit of integration. Okay, so if I put f prime of x dx in there, from the fundamental theorem of calculus, this is equal to f of 4 minus f of -6, which once again we know is f of 4 plus 2 from here, which implies that if I'm trying to find just f of 4, it's equal to -2, subtract the 2 over here, plus this integral, -6 to 4, f prime of x dx. And once again, we interpret that definite integral as an area, but this time there's more area that's being accumulated. We're going from -6 to 4. Here's 4 right here on the x-axis, right? So I'm going to cut that like that. And I need to break this thing up because I'm looking for all of this area now. I need to break it up into manageable chunks where I have geometric area formulas that I can use. So actually, let's put these two parts together. I'm going to call this whole thing here just one big rectangle. So you can kind of ignore this line. We already know the area of that triangle. Oh, I also need the area of this semicircle down here. The area of that triangle, and actually the area of all of this stuff that we're accumulating, is all going to be interpreted as negative area because it's all under the x-axis. So we'll be putting minuses there. What is this equal to? So -2. We've already seen that the area of that triangle is -6. That's from this right here. So let's just write -6 there. This rectangle right here has a base of, let's see, it goes from -3 all the way to 4. So that's a length of 7. And then the height we've already seen is the same as the height of this triangle. The height would be 4. So 7 times 4, but we subtract that, -7 times 4. We have this triangle down here, which goes from, it looks like -4 to -6. So that's got a height of 2. And then here it goes from 1 to 4. That's got a base of 3. So -1/2 base times height. And then we have this semicircle right here. So the diameter of this semicircle, well, actually, we can either use the diameter or we can use the fact that if I go from here to here, that's the radius. That goes from -4 to -6, which means that has a length of 2. So radius of 2. A semicircle is half the area of a circle. So 1/2 pi r squared, 1/2 pi times, I said 2 squared, right? Notice I'm putting minuses in front of all of these areas because they're all under the x-axis, which means we interpret them as negative. So what do we have here? -8 minus 28. 6 times 1/2 is 3, so that's -3. And then 2 squared is 4, times 1/2 would be 2, so this is -2 pi. We're going to leave the -2 pi alone, but we'll add up the rest of this stuff. This is -11 plus -28, that's -39. So -39 minus 2 pi is the answer for that one. Okay? All right. So that's, again, still using the fundamental theorem of calculus part 1, but we're interpreting things as areas here instead of just net change, which is how we've been kind of thinking of it in this section. There's more to come, so we're going to keep going in the next part.